All right. So good morning. Good to see you guys. We are talking today about something called the mole concept. A mole is a counting tool. It's something that's going to be helpful, especially for counting things that come in extremely large quantities. All right. Like, for example, atoms. Hey, I want to tell you guys, some of the things that I have on the screen you'll need to write down. Some of them you will not. What I'm going to try to do is I'm going to try to highlight for you. If I highlight it, then you need to write it down. Okay? But then there's some things that are just a little bit extra. All right? So let's take a look. There are some different ways to measure items. Ways that we can measure items. And we can measure them by count, by mass, or by volume. Hey, I'm going to go back and talk. I know that's faster than you can write. By count, for example, if I were going to buy some apples, I might go to the store and I might say, hey, can I have 10 apples? Well, that's a count because they're just going to count out the 10 apples. Another way that I could buy them, if I go to Walmart or H-E-B and I want to buy some apples, is I could buy them by mass or by weight. And if I bought, for example, 1 kilogram of apples or 2.5 pounds of apples, then that would be another way that we could have the apples counted. A third way that's less common, at least less common, for us as consumers, is by volume. For example, I don't know if you guys are aware, but a lot of farm produce is sold by bushels. A bushel of grain or a bushel of produce or a bushel of whatever. 1 bushel is equal to about, that's like one of those big baskets, as a bushel basket. And that is equal to about 35 liters. We're used to using liters for liquid, but it's actually a measure of volume. Okay? And so when we talk about 35 liters, that's about 35 of the regular Gatorade bottles. All right? So that's a 1 liter, 1 liter Gatorade. And so that's that. So those are just 3 different ways that we can count and measure items. Now, for apples, that's all good. I can count out 10 apples. I can mass out 1 kilogram, or I can, get a certain volume of apples. Hey, but let me ask you this. What about carbon atoms? Now, if I told you to mass out some carbon atoms, if I said, hey, we need 17.2 grams of carbon, hey, you get your scale out and you mass it out and you're all good. You can do that. If I tell you, hey, we need 4.1 milliliters of carbon, all right. Well, you could, or if I told you a certain number of cubic centimeters of carbon, you could make that happen. All right, you could get the carbon measured that way. What if I told you that we needed to count the carbon atoms? What if the next lab we did, I said, hey, you need to start with 250 carbon atoms. Whoa. How are you going to count out 250 carbon atoms? Can you do it? No, you can't. Okay, I started to say, can you do it? But somebody, go ahead and answered, yes. No, you can't do that. How do you count atoms? All right, they're too small. For example, like you're like, hey, we'll just put like the smallest little pencil dot that we can, and maybe that'll be close. If you put the smallest pencil dot, of graphite, carbon atoms, you would have like billions and billions of carbon atoms. Okay? You would not have 200. You would have millions and billions. All right? And so atoms are so small that in order to count them, we need a special unit. And that is where the mole is going to come in. And so the mole is a counting unit. Hey, you guys have heard of a dozen. How many's in a dozen? Whoa. Have you heard of a gross? A gross is a dozen. So that's 12 times 12, so that's 144. What about a mole? That is not the cute, cuddly little garden animal. They're not cute and cuddly anyway. They're kind of ugly. All right? But this is not the garden animal. This is a counting unit called a mole. And it is equal to 6.02 times 10 to the 23rd items. Just like a dozen is 12 items, this is 6.02 times 10 to the 23rd items. Hey, that is a 6 followed by 23 zeros. All right, that's a lot. All right, that's hard to wrap your mind around, and that's why for example, I'm just going to give you an example. Let's see. Hey, if we all got that the mole is a counting unit and that this is how many items it's equal to? Yeah, we're good there? All right. Hey, by the way, the abbreviation for a mole is just MOL. You can drop the E, and that's an abbreviation, so I'll start using that in our presentation. Here I actually typed it out, 6.02 and then 23 decimal spots. So it's that many items. If I took ordinary marbles, like the basic little glass marble, and was going to circle the Earth at the equator with marbles, how many times do you think I could go around the Earth if I had 1 mole of marbles? Once? Twice? A couple of hundred? A couple of thousand? You could go around the Earth so many times that you would have a layer of marbles 3 miles deep. I'm not messing with you. That is how many items we're talking about. That is more than you can really wrap your mind around. Okay? But I'll just put that out there for you. Hey, I want you to know that the mole is defined as the number. Hey, remember we're defining a number, okay, like a dozen is 12. A mole is the number of atoms in 12 grams of carbon-12. So it is exactly the number of atoms, or it is the number of atoms in exactly 12.00 grams of carbon-12. Hey, you remember when I put the isotope, when I put that number up there, that means it's a particular isotope. All right, carbon-12 is the isotope of carbon that has a mass of 12. That is 6 protons and 6 neutrons. Now, this number, okay, for this measurement was determined experimentally thanks to the work of a gentleman named Amiato Avogadro. He was Italian. All right. And his work helped us define a mole as this many items. And so because of that, we call 6.02 times 10 to the 23rd, we call that Avogadro's number. And I do want you to write that down. All right? And so we call 6.02 times 10 to the 23rd Avogadro's number, and that is the number of atoms, or the number of items, in 1 mole of something. All right? We feel good about that? Questions so far? All right, excellent. I'll give you a second. I'm kind of watching to see how people are doing with their writing. And again, if I go too fast, you let me know and we can go back. And also this will be, the slideshow will be posted in Google Classroom along with this recording. All right. Hey, so we're going to do a little math here. How many moles of phosphorus are in 1.20 times 10 to the 25th phosphorus atoms? So go ahead and write down that problem. How many, we'll use some Panther Purple. How many moles, we need a thicker line. How many moles of phosphorus are in this many phosphorus atoms? If I have that many phosphorus atoms, how many moles do I have? If I have this many phosphorus atoms, how many moles do I have? No. Okay, hang on. We're gonna do the calculation. We're gonna find out. Hey, let me ask you this: have you guys seen this dimensional analysis grid before, where we set things up and do some multiplication? All right, I got some back and forth. No. Any up and down? Yes. All right, a lot of back and forth. No. Hey, yeah, and that's fine. So I'm going to introduce you to this grid because this is the way that I like to work the problems. You always put what you start with right here. So this is your start. Okay? So you're going to start with what you're given. You start with what you're given. And we were told that we had 1.20 times 10 to the 25th phosphorus atoms. So I'm going to write down 1.20 times 10 to the 25th phosphorus atoms. Now, you guys are good with algebra. Okay? You've heard of it. You've worked with it. What can I multiply a number by and not change its value? 1. Excellent. So I can multiply something by 1 and not change its value. So what I'm going to do is I'm going to multiply this number that I started with by 1. You're like, Mr. Willis, that is not a 1. That is a weird fraction. Yes, but you remember something else about fractions. If I have two equivalent amounts divided by each other in a fraction, that counts as 1. So if I have 4 over 4, that's really 1. If I have 732 over 732, that's really 1. Good, yes. All right. Hey, check this out. So what I've done here is I've written two equivalent terms. You remember that we said 1 mole of anything was 6.02 times 10 to the 23rd of that thing. So 1 mole of phosphorus atoms is equal to 6.02 times 10 to the 23rd phosphorus atoms. So really this is a fraction that is equivalent to 1. All right? So I'm really taking this and I'm multiplying by 1 so that I'm actually not changing its value. I'm just changing its unit. All right? It's kind of like when you have to change denominators in fractions. Like if I had something in eighths and I need to change it to 24ths, I would multiply by 3 over 3. Yeah? Yeah. So in this case, I have phosphorus atoms. Hey, take a look and watch the magic here. I have phosphorus atoms. And so what I'm going to do is I'm going to put this number that also has phosphorus atoms in the denominator, in the bottom, so that when we do the math, these units will reduce away. And I'll be left with this unit. Okay? So I started with this many phosphorus atoms. I'm going to multiply by 1 mole of phosphorus atoms, which is equal to or equivalent to 6.02 times 10 to the 23rd phosphorus atoms. That and that are going to divide away, and I'm going to be left with moles of phosphorus atoms as my unit. Oh, Mr. Willis, how did you get the number? I'm glad that you asked. I took my starting number and then divided by this number, okay, because these are on the top and the bottom of a fraction. All right? Hey, do we feel good? Are there questions about the process? Do I need to run through it one more time?
At first I was confused, but then I got it, because I was like, where did you get this 6.2? But it's the Molar formula.
Exactly, that's the mole formula, because that's equal to 1 mole of items. Excellent. Where did I get this?
Because that's the mole of phosphorus.
This is what we were given to start with. We were starting with that.
Oh, I mean at the bottom where it says 6.02, why don't you put the other number?
Oh, I could have put the other two. I chose to only use 3 significant figures instead of 4, but I could have just as easily put that 4th one in there, and it would have changed the answer just a little bit. But again, I just chose to use 3 significant figures, so that's the only reason I left the other 2 out. No, it would not be wrong. And in fact, most people are going to say 6.02. Most people are going to do 3 significant figures. All right? Hey, now, everybody take your calculator. All right? And I want to show you how to type scientific notation into these calculators in case you don't know. All right? So turn it on. Hit the on button. And hit the on button a couple of times, and you'll be at your home screen. And then if you look on the left, there's this, the left kind of at the top, there's this button that looks like a flying calculator. It's got a calculator with a couple of lines past it. It looks like it's got a little cape or something. All right, push that, and that will take you to the scratch pad. And the scratch pad is where you're going to do your calculations. All right, hey, here's how we're going to enter scientific notation. I want you to type in 1.20, and now we're going to type in times 10 to the 25th. Don't type yet. You see the button, there's a button with a double E. It's on the left, it's toward the bottom, right under the parenthesis. On the left, toward the bottom, right under the parentheses. You see that double E? Push that, and it's going to stick a capital E into your calculation line. And that capital E means times 10 to a certain power. Hey, what power do we need to put in there? 25, 25th power. So just type in 25. And now I want you to hit divided by, and I want you to type that again, 6.02, and then hit your double E button, and then 23. Hit enter, and see if you don't come up with 19.9 and some change.
What after the
6.02, and then hit the double E button, and then 23, because it's times 10 to the 23rd. Hey, look at the screen for a second. You see the times 10 to the 23rd? That's where we got that 23, and so that's why you put 23 after the double E.
Okay.
All right, what was the question here? We good?
And then what do we divide it by after the
Well, that's what we were dividing by. Again, because you see that we've got this number on the top. All right, got this number on the top. And then we're going to divide by this number that's on the bottom. Yeah, sometimes we'll multiply, and that'll be fine. You do it the same way.
Wow, that's so much more easier than putting times 10.
Oh yeah, it is. I love my little double E button. Okay, it's a great tool. All right, hey, we good? We feel good about that? We feel good about our 19.9? Guess what? Oh. How many moles of Mg are in 3.01 times 10 to the 22nd Mg atoms? Oh, I was going to ask you what Mg stands for. Yeah, magnesium. I gave it away. You knew though already, didn't you? Good. You guys are bright. Hey, so the first thing I'm going to do, I'm going to give you a chance to copy that problem. I'm going to go ahead and draw my little grid. I'm going to draw my big fat line in the middle. All right. Now I'm going to put what I start with right here. It says how many moles of magnesium are in 3.01 times 10 to the 22nd magnesium atoms. Ooh. So you were getting ahead, man. You were right though. Hey, just keep watching. 3.01 times 10 to the 22nd, and that's magnesium atoms. Because I'm going to show all my work so that everybody can follow along. All right. Now, I want to finish with moles of magnesium atoms. That means that I'm going to want my moles to be up here, and I need to divide out the actual number of magnesium atoms. So in 1 mole of magnesium atoms, 1 mole of magnesium atoms. How many magnesium atoms do I have? I'll give you a hint. Yep. Avogadro's number, 6.02 times 10 to the 23rd magnesium atoms. Let's just get my line on out there. There we go. Hey, so here's what's going to happen. When I multiply across this number times 1, I'll get a value. And then when I take the bottom and multiply it across, and then we're going to divide everything by whatever we have in the bottom, my atoms are going to go away, and I'll be left with just moles. So 3.01 times 10 to the 22nd times 1 divided by 6.02 times 10 to the 23rd. Hey, you don't really have to multiply times 1. You guys are bright enough to know that that's the same. You already told me. All right? Hey, do that math and tell me what we come up with. Yeah, 0.05. Now, what units? Moles of magnesium. Excellent, excellent. Well, in this case, you mean like up here? I like, when I'm doing it this way, I always include my units so that I can know what goes in the top and what goes in the bottom. Because otherwise I will mess it up and I'll multiply when I should have divided, or I'll divide when I should have multiplied. So doing it this way helps me see where my units belong, and that helps me get my numbers in the right spot. Now, I don't, you don't type your units into the calculator, but you always have to have your units. All right. Hey, do we feel good about that? Now, let me show you this. This was going from moles to atoms. Okay? We started with moles, we went to atoms. Now we're going to start with atoms and go to moles. That's right. Hey, let me ask you this. What do you think the difference is going to be?
Multiply.
Yes, you're going to multiply. Hey, here's what that looks like on the screen. You see that what happened is this part of my fraction got turned upside down, because now I'm starting with moles, which means I need to have moles in the bottom. And so I'll have this on top, and I'll multiply. So let's do that real quickly. Go ahead and write down this problem. How many atoms of zinc are in 0.750 moles of zinc? How many atoms of zinc are in 0.750 moles of zinc? So you're going to write down what you started with. We started with 0.750 moles of zinc. And then we're going to write our equivalent fraction, which is going to have Avogadro's number at the top with the zinc atoms, and 1 mole in the bottom with zinc atoms. And that's right here. And when I do that math, my moles of zinc are going to go away, and I'm going to be left with just zinc atoms. And that's going to be what I get when I multiply 0.750 times Avogadro's number. Somebody check that and see if I got the right answer.
Yes.
All right, excellent. I have a confirmation. We feel good for that? All right, excellent. All right, there's a question. Go ahead. Does it matter which one you mark out? Okay, so it does matter. You have to cancel out the ones that are equivalent. And so it's the fact that I had moles of zinc here and moles of zinc here. And really I could say moles of zinc atoms and moles of zinc atoms, and so really it's my units down there and my units here. And notice that in order for them to cancel out, they have to be in opposite sides of the fraction. They have to be in the numerator and the denominator so they can reduce away. Okay? Yes, ma'am?
So in the calculator, you put 0.750 times 6.02 equals 23?
Yes. So in my calculator, I would put 0.750 times 6.02, and then I would hit my double E button. That may be my favorite button on the calculator. 23. And then the way it will read out in your calculator is it will read 4.52 E 23. All right? And that E again means times 10 to the power of. Times 10 to the power of. All right? Hey, questions? You guys are doing excellent. We are moving on. Ooh. How many atoms of gold are in 8.50 moles of gold? All right. So I'm going to start with my big line. And I'm going to start with what I'm given. And that is 8.50 moles of gold. And I'm going to give you a moment and see if you're able to fill that in correctly. All right, doing great. Write that down. And now we're going to put in our equivalent fraction. And what are we going to have on the bottom so that it will divide away? Yeah, 1 mole of gold. But I need to put something equivalent on the top. Well, equivalent to 1 mole is 6.02 times 10 to the 23rd atoms of gold. All right, and so you guys do the math and let me know what we get. And that will tell us how many, see, I'm going to go ahead and cross that out.
Times 10 to the 24th.
Tell me again.
5.12 times 10 to the 24th power.
Anybody else get that also?
I got 5.1170.
Ah, okay. So if we round to 3 significant figures, then that would be 5.12, right? All right, excellent. Times 10 to the 24th. And that is what units? Yeah, atoms of gold or gold atoms. All right. Very good. Well done. We'll finish recording all that, finish getting that copy down, and then we will move on. Well, they're the same. That's kind of like saying, are there 12 eggs in a dozen, or in 1 dozen are there 12 eggs? Okay, so here's what I'll tell you, is that there are 6.02 times 10 to the 23rd atoms in 1 mole. So 1 mole has that many atoms. Did I answer your question, or was it a different question? The way that I know when to multiply and when to divide is I look at what I was given. In this case, so I look at what I was given. In this case, that was moles. And since I want to get rid of that, I need to put it in the denominator. I need to put it on the opposite side so that it will reduce away. Okay? So that's how I know which one goes on top and which one goes on bottom. I look at my units. All right? That's an excellent question. All right. So I got a question for you guys now. All right, I've answered your questions. Now you answer mine. Riddle me this. So, a dozen is a dozen, right?
Yes.
Yeah. Dozen eggs, dozen elephants, same? Oh.
No.
Oh, okay. Yes, no.
One is egg, one is elephant.
Okay, yeah, one's eggs, one's elephants. Thank you. Hey, here's the thing. A dozen is a dozen? Yes. They're both 12. But also, no. Because the elephants weigh way more than the eggs. So even though it's the same number of items, it's a very different mass, right? Hey, and you guys knew that. I didn't, when you came in here, you didn't think that a dozen of everything weighed the same. You know better. Okay? Here's what I want to mention to you though. So even though the numbers are the same, there's different amounts of mass. So let's think about that. So is a mole always a mole? Well, yes. 1 mole of helium atoms is 6.02 times 10 to the 23rd atoms. 1 mole of carbon atoms is 6.02 times 10 to the 23rd atoms. But the carbon weighs 3 times as much. If you look on the periodic table, you'll see that carbon has an atomic mass of 12 and helium has an atomic mass of 4, if we round them to the whole number. Okay, so I rounded to the whole number because that's the most common isotope. And we know that real atoms don't have fractions of neutrons, or don't have decimals of neutrons. So even though 1 mole is 1 mole in terms of number, they're different in terms of mass. And that's what I...
That riddle, that's like, which one's heavier? A pound of...
Yeah, a pound of gold or a pound of feathers. Okay. Yeah, and in that case, it's actually talking about the weight being the same, but the number and the amount would be different. In this case, we're talking about the number and the amount being different. You know, if I said, which has more, 12 eggs or 12 elephants? Well, they both have the same number, but which one weighs more? Yeah, it's going to be the elephants. Okay? All right. So a mole is a mole, meaning that 1 mole will always have the same number, but the mass is different, and that's going to be what we call the object's molar mass. Okay, so I want you to write that down. Oh, we need to go back up for a minute. Okay. All right. Hey, I'll go back up. I'll go back up in just a second and let you get it. The mass of 1 mole of something is called that object's molar mass. Mr. Willis, where did they get this word molar mass? It's the mass of 1 mole. So however much 1 mole of anything weighs, that is that item's molar mass. Or I shouldn't say weighs, I should say however much mass it has. Go and let you get it. All right. So, hey, don't write this yet. I'll show you what to write here. You remember that 1 mole of carbon was defined as the number of atoms in exactly 12 grams of carbon-12. So the molar mass of carbon is 12 grams. Here's what I want you to write down. The molar mass in grams for any element is equal to its atomic weight in AMUs. Molar mass in grams for an element. Molar mass in grams for an element is equal to its atomic weight in AMUs, or atomic mass units. You remember that carbon has an atomic mass of 12. That means 1 mole of carbon is 12 grams. Nitrogen has an atomic mass of 14. That means that 1 mole of nitrogen weighs 14 grams. Oxygen has an atomic mass of 16. That means 1 mole of oxygen has a mass of, 16 grams. Hey, everybody with me? Hey, if I tell you that calcium has an atomic mass of 40, then that means that 1 mole of calcium has a mass of 40 grams. All right? 1 mole of anything has a mass of whatever its atomic mass was, but in grams. Thumbs up? All right, excellent. Let's see. Ooh, I want you to copy this whole slide. Hey, you see this part here where I wrote the isotope number? You don't have to write that. If you just want to say 1 mole of helium is 4 grams and 1 mole of carbon is 12 grams, you can. And 1 mole of gold is 197 grams. But here's the deal. All of those are 6.02 times 10 to the 23rd atoms. So all of those, even though they have different masses, they're the same number of atoms. Now wait, how come you have to have 197 grams of gold to have the same number of atoms that you do in only 4 grams of helium? Tell me again.
Weighs more?
Other way.
Gold.
Yeah, because gold is a much bigger atom. Hey, gold has a lot more protons and a lot more neutrons and a lot more electrons. Gold's got more stuff in there, so each atom weighs more. So you got to have more mass of gold to get the same number of atoms. That's just like I got to have more mass of elephants to have the same number, if I'm getting dozen. Questions about that? All right. Now, so far you guys think that I'm pretty much perfect and amazing in every way, right? Yes? Excellent. Good. That was good. Hey, there's a mistake on this next slide, all right? So I'm sorry. I didn't want to let you down too hard, all right? So there is a mistake on this next slide. I'm just going to tell you in advance. Do you see what it is? All right. This is our example. All right, let's see. Yeah, did we find it? Hey, so the question says, how many grams of nitrogen in 7 moles of nitrogen? So here we put what we started with. Oops, except I put the decimal in the wrong spot. It ought to be there. So just ignore that little thing. That's bugging me. I wish I could get rid of it. But, hey, it's good to be faced with your own imperfections sometimes. All right, how many grams of nitrogen in 7 moles of nitrogen? Again, we can do grams to moles. We can do moles to grams. So I'm going to start with what I'm starting with, 7.00 moles of nitrogen atoms. And I'm going to put here my equivalent conversion. All right, my equivalent fraction. Again, I'm going to put what I want to get rid of on the bottom across from it. All right. So I started with moles of nitrogen atoms. I need to get rid of moles of nitrogen atoms. So I'm going to put 1 mole of nitrogen on the bottom. Ooh, and it's 14 grams because I looked on the periodic chart and I saw that the atomic mass of nitrogen is 14. So when I take 7 and multiply by 14, I will get, yeah, excellent, 98 grams. Those will go away, and I'll be left with just grams of nitrogen atoms. All right, and again, we're just going to ignore that little. That's great. That looks like there's 2 decimals now. There we go. All right. Hey, so 98 grams of nitrogen atoms. We're good there? All right. We're still writing, but we're good. We understand? Excellent. Next question. How many moles of iron are there in 74.565 grams of iron? Hey, so I've just brought in like a small handful of iron. All right, almost 75 grams. And I want to know, hey, how many moles of iron I got here? So we're going to take what we started with. We're going to put it here on the top. We're going to set it up so that our units cancel. I want to get rid of grams of iron atoms. So I'm going to put down here grams of iron atoms. And then I'm going to fill in my equivalent, 1 mole to every 56 grams. Where did I get that? I looked on the periodic chart and saw that iron has an atomic mass of 56. So 1 mole of iron atoms, 56 grams. When I do that, my grams will go away. I'll be left with moles of iron atoms. And we'll do the math. That times 1 divided by 56. And we should come out with 1.33. All right, try that out. See what we got. We good? And you guys are doing excellent. Okay. I know that we've covered a lot of material. All right, and we still have some more to go, so don't give up yet. All right, you're doing good though. I want you to know that. Why did the elephant paint his toenails red? So he could hide in the cherry tree. You ever see an elephant hiding in a cherry tree? See, it works. Okay, all right, that didn't go well. All right, hey, more elephant jokes later. You guys will love my elephant jokes by the time the presentation's over. Promise. Hey, what about molar mass of compounds? All right, so let's write this down as a slightly new, slightly different topic. Up until now, we've only been talking about atoms. We've talked about atoms of iron. We've talked about atoms of nitrogen and carbon. What if it's not an atom? What if it's a compound, like sodium chloride? All right, hey, I'm going to go to the next. We're still in the same topic. Now, I want you to think about this. If I have 1 mole of NaCl, what is that made up of? Okay, that's an ionic compound. It's sodium chloride. What is sodium chloride made of? This is not a trick question. Sodium and chlorine. Excellent. Okay. Hey, sodium chloride is made of sodium and chlorine. So if I want 1 mole of sodium chloride, that's going to need 1 mole of sodium and 1 mole of chlorine. Oh, well, if I look on the periodic table, what's the atomic mass of sodium? 23, that's right. So 1 mole of sodium will be 23 grams. What's the atomic mass of chlorine? 35. Okay, so that means that for 1 mole of chlorine, I would need 35 grams. And I mix that up and react it. All right, and I get 1 mole of sodium chloride, which has a mass of 58 grams. Mr. Willis, where did 58 go? 3 plus 5 is 8. 2 plus 3 is 5. We didn't even have to carry the 1. All right, so let's copy that slide. Be sure that we understand that.
So you basically just add the 2 grams to...
Yeah, you just add the 2 parts together. Okay? If I've got sodium chloride, it's made up of sodium and chlorine. And so I'm going to add the value for sodium to the value of chlorine. All right? Ooh, but what if... Dun, dun, dun. All right? I'm going to let everybody finish copying this down, then I'm going to do my what if. I kind of spoiled it. I already used my, dramatic music, and now I have to wait and stall while everybody finishes writing. It's okay. It's what I do. I'm a teacher. I'm very good at it. I can stall as long as I need to. All right, I think we're about done. Hey, so let's write this down real quickly. So my dramatic music was actually a slide early. So the molar mass of a compound is equal to the sum of the atomic masses of the atoms in the formula. Molar mass of any compound is equal to the sum of the atomic masses in its formula. All right. And that's what we just did. That's what we just did previously. We wanted to know about 1 mole of NaCl. Well, that's made of 1 sodium and 1 chlorine. So I said, hey, that would be 1 mole Na plus the mass of 1 mole of Cl, and that would give me the mass of 1 mole of sodium chloride. All right? We're feeling good about that? All right, excellent. All right, now cue dramatic music. But, dun dun dun. What about carbon dioxide? What's different?
It has 2 carbons.
Ooh, okay, yeah, number 1 is carbon. But also, there is a 2. All right? Yeah, which means that is not a big deal. Since that 2 tells us that there are 2 atoms of oxygen, then that means that we need to multiply its molar mass by 2. So since it has 1 atom of carbon, we're going to do 1 times 12, which is the molar mass of carbon, or excuse me, the atomic mass of carbon. And then since we have 2 atoms of oxygen, we're going to multiply its mass by 2. Hey, again, that makes sense, because if you have to have 2 atoms of oxygen for every 1 atom of carbon, that would mean you would need 2 moles of oxygen for every 1 mole of carbon. And so the total molar mass then will be, let's see, 1 times 12 is 12, 2 times 16 is 32, 2 plus 2 is 4, 1 plus 3 is 44 grams. So the molar mass of any compound is just found by counting the number of atoms in the compound, multiplying each number by that atom's atomic mass, and then adding them all together. So again, you're just taking the parts and valuing them separately, and then combining them together to get one overall answer. Yes, someone has got some shoes that they're very proud of in the hallway. They are squeaking the dog out of them. That's why I don't teach middle school. All right. Hey, we ready? So what about the molar mass of glucose? Okay, one of my favorite compounds. Glucose, it's a form of sugar. Now glucose is C6 H12 O6. So you see that means that I need to find the mass of my carbon. I need to find out how much carbon I would have to have. And since carbon has a molar atomic mass of 12, I'm going to say 6 atoms times 12 AMU per atom. Okay. What's 6 times 12? 72. Good, good. We got some math scholars. So 6 times 12 is 72. All right. 12 times 1. Okay, good. You guys are really good with your 12s. That was fast. All right. 6 times 16.
96.
Oh, good job. Add them all together.
That's 180. I think.
Okay, add them.
No. 1, yeah. No. 190.
Do the math. I'm getting 180.
Yeah, 180.
Hey, you got a calculator on your desk. Don't be scared. That is 180 grams per mole. Hey, check out the units for this. It's grams per mole. All right? Because we need to talk about how many grams there are in 1 mole of material. All right? Hey, I got another one for you. We good there with our 180? Hey, here's another one. One of my favorite compounds, caffeine.
I just had some this morning.
I know. I am under-caffeinated currently. I have not had enough coffee this morning. So, so let's see. So for my carbon, I would have 8 atoms times an atomic mass of 12. For my hydrogen, I'm going to have 10 atoms times an atomic mass of 1. For my nitrogen, I'm going to have 4 atoms times an atomic mass of, I'll go ahead and tell you that it's 14. You could look on your periodic table. And then finally, for my oxygen, I'm going to have 2, and they are 16 each. Okay? So everybody do the math and add that up. Let's see, that's 96. Ooh, 10 times 1. Carry the 1. Okay, there we go. 4 times 14 is 56. This is going to be 32, and the grand total of them all is 194 grams per mole. Excellent, excellent. Very good job. All right, 194 grams per mole. All right, let's see. So what we're going to do is I'm going to pause our recording here for a moment through the magic of video and vision. All right, and we are back to continue our percent composition by mass. So I want you guys to consider water. If I asked you how much by percent, how much of water is hydrogen, what would you say? Would you say, well, there's 2 atoms of hydrogen and 1 atom of oxygen, so that's like 2/3 hydrogen? But we know that hydrogen is like a lot less massive than oxygen. Oxygen has a lot more mass. All right? And so what we need to do is we need to think about this, and we're going to think about this in terms of mass. So when we say what is the percent mass of hydrogen in water, we need to consider it this way. Okay, we are going to consider, when we talk about percent composition by mass, we need to know how much mass of hydrogen there is compared to how much mass there is in the whole molecule. Okay? And so again, this is going to be a percent, and any percent is part over whole. All right? So we're just going to look at we need to know how much mass of hydrogen there is compared to the mass of the whole molecule. All right? So to find that out, so for water, there's 2 atoms of hydrogen, so 2 times an atomic mass of 1. And then there's 1 atom of oxygen, so 1 times an atomic mass of 16. Now 2 times, let's see, get my math out. 2 times 1 is 2. 1 times 16 is 16. All right, so I add those up for a total of, that's right, 18. So total of 18 units. And remember that we wanted to know the percent composition of hydrogen. Okay? So I need to say, hey, how much hydrogen is there in the whole molecule? Well, there are 2. Okay? So 2, so the mass of hydrogen, the mass of all my hydrogen is 2. The mass of my whole molecule is 18. And when I do the math there, I will get 11.1%. Remember, you're actually going to get 0.11111 repeating, but when you multiply by 100 to convert to percent, you'll get 11.1%. If you need to pause the video to write any of that down, you may. All right. So what is the percent composition by mass of nitrogen? Okay, so percent composition of nitrogen in calcium nitrate. Ooh. And I just want you to look at what the problem is, okay? I want you to look at everything that's above the black line. What's the percent by mass, the percent mass composition of nitrogen in calcium nitrate? And some of you guys are like, I don't know, what's the chemical formula? Oh, what did we just finish talking about? That's right, chemical formulas. And so if you do not know how to write a chemical formula, you are going to be in trouble. You need to go to tutorials and figure out about chemical formulas. All right? So start with the chemical formula, which for calcium nitrate happens to be CaNO3 All right? 1 calcium atom, 2 nitrate ions. All right? Polyatomic ions. Now, so let's do the math for that. So in calcium nitrate, we're going to have 1 calcium, which is an atomic mass of 40, 2 nitrogen, so that's 2 times an atomic mass of 14. Ooh, why 2? What I want you to see is this nitrate, this whole yellow ion is multiplied by 2. So 2 times 1, okay, remember there's an implied 1 here. 2 times 1 means that there are 2 atoms of nitrogen, multiplied by 14 for its mass. Oxygen, there's 3 in each nitrate, but there are 2 nitrates, which means there are 6 oxygens. So 6 oxygens, 6 times 16. When you multiply all that together, the total mass of calcium nitrate, okay, its formula mass or molecular molar mass is 164 units. Okay. So the percent nitrogen, well, remember nitrogen was 2 times 14. So that ends up being 28. So there are 28 units AMUs of nitrogen for every 164 AMUs of calcium nitrate. And when you do the math of part divided by whole, you will get 17.1% nitrogen. Excellent. All right, at this point it is practice time. So thanks so much for hanging with me today, and I hope you have a great afternoon. Bye-bye.